This video will help you to derive the kinematic equations, as well as to figure out how to do your error calculation for the lab. The first thing I want to mention is these are the three graphs that you need to have. You have your dt, which should be a curve, you should have your vt, which should be a line, and you have your dt squared, which should also be a line. This is one way that we can use to manipulate our data in order to straighten the curve to a line so that we can analyze it using the line equation. Now, let's start with the VT equation. This one's going to be the easiest to work with. So we have a VT graph that is a line, and in this case, we know what the value of the slope means for us. So you'll have a number value, but we want to talk about the meaning of the slope. The slope of a VT graph is our acceleration. So we know that this slope is the acceleration. Now, if we were to use our line equation, so we have y is equal to mx plus b. If we look at this, our y is our velocity, and that's going to be equal to the slope, which is our acceleration, times our x variable, which is time, plus the y-intercept, which in this case is going to be our v naught, and that's what it's going to look like. Now, this v in particular that we typically use is going to be our vf. Our v final is equal to at plus v naught, or we can move these around a little bit. Now, the way to think about it is this over here is our v naught, and there'd be a point over here which would be our vf, and that vf would be determined by this equation. So that's the first derived equation. Now, what I want you to do is I want you to look at your dt squared graph and compare the slope value to your vt graph. And this is where we're going to see how well you did your lab. What you should notice, first of all, is that the slope of the dt squared graph is less than that of the vt graph. In fact, it should be by a factor of 2, or in this case, this value should be 1/2 of your slope value here. And this is how you're going to calculate your error. What you will do is you will multiply the slope value from your dt squared, multiply that by 2, and then you'll do your percent difference calculation between those two a values. So in this case, with our lab, we are finding our acceleration through our vt graph and our dt squared graph, and then comparing those two values to see how well we did with our lab. Now, what I want to derive for you, though, is from here, we can see that we have another line, so we can again use our y equals mx plus b. And now we just do the same thing that we did before. Our y is our displacement, and that's going to be equal to our slope, which is 1/2 a, times our x variable, t squared, plus our y-intercept, which in this case is d0. Now this is where things are a little bit different than what I've shown you before. In fact, in this case, we are missing a term in this, and that's because of the way we created this graph. By simply doing a t squared graph, we are losing some information, and so we can't get that from here. And in fact, we usually have the d0 eliminated, and what we usually put in its place, or what we put there, is 1/2 at squared, and then rather than d naught, we put a v naught t. And so we typically get rid of the d0, d naught, and it becomes the v naught t. There is more math behind this, but for right now, that's going to be good enough. Now, the next thing I want to talk about is average velocity. And we denote it by a v with a horizontal line above it. Now, the equation that we've worked with so far is v is equal to d over t. And we can say that this is the average velocity is equal to the total displacement divided by time. That's one of the average velocities. But the other average velocity that we can work with is what we traditionally think of as the average of anything. In this case, it's going to be our vf plus our v naught divided by 2. Now, for both of these, the assumption is that our acceleration is constant. So we cannot use a variable acceleration, but for all the problems that we're going to be working on in this class, our acceleration will always be constant. Now, I'm going to show you a couple of derivations using these equations as well. So let's bring it down over here. The first thing that I want to go through is this part over here that I want to highlight. So we have v is equal to d over t. We can move the t over. So it's TV is equal to D, and then T is equal to D over V. That's the first manipulation. And then we're going to use our VF is equal to AT plus V naught, move the V naught over, so it's VF minus V naught is equal to AT, and then T is equal to VF minus V naught over A. Now, what you'll notice here is that I have isolated T for both of these, so I'm going to set these two equations equal to each other, or you can think of it as a substitution, and that's where we get this. D over V average is equal to VF minus V naught over A. From here, we are going to substitute in what we know for V average down here. So we're going to plug that in. So from what we went through over here, for V average, we plug that in to that over there, so we get VF plus V naught over 2. When we simplify this, we move this 2 to the top, so it's 2D over VF plus V naught is equal to VF minus V naught over A. We're going to cross multiply, and that gives us 2AD is equal to VF squared minus V naught squared. If you do your FOIL, you'll see what happens to the other terms. We can talk about this more later. And when we rearrange this, we get VF squared, we move the V naught to the other side, is equal to V naught squared plus 2AD. And that's one of our other kinematic equations. For the last derivation, we're using the two V averages again in a different way. And we can see that right now they're both solved in terms of V average. So we can just set these two equal to each other. And so we get VF plus V naught over 2 is equal to D over T. And we can move the 2, factor it out, so it becomes 1/2 times that over there. And now, when we rearrange this, we just get D is equal to 1/2 times VF plus V naught times time. And those are our derived equations. Now, as a quick reminder, for the lab, you're going to do your percent difference calculation, which is given to you in the OneNote file. You will multiply the dt squared slope by 2, and then compare that to the VT slope to compare your accelerations. And that'll be it.